So in this part, we will deal with the uncertainties and the measurements that we have studied associated with the physical quantities that we have defined in our earlier classes. So in this part, we will study with what are the significant figures, how we assign the number of significant figures to a values, and how they are taken into account when you make some measurements. Then we will proceed on to discuss about the dimensional analysis part, which is merely an extension of the units, and that we will see in the later part of the discussion. We will also try to cover the vectors and how the vectors are being added, how it is different from the scalars that we have studied in your last class, and then we will proceed on to discuss with the numericals. Let's move to the next subtopic, that is uncertainty in the measurement. Now, whenever we make measurement, we have been doing measurements all the time. We have been dealing with how do we measure things, how to put them in a quantitative manner. Now we will see when we do the measurements, we know we cannot have a certain value. There is no such thing as a perfectly accurate measurement. Like if you measure the length of a thread with a scale, you will have some uncertainty, like 21.6, suppose something that I don't know, you are not sure, you may write that value, but you are not sure of that value. So there is always an uncertainty in the measurement. Now this uncertainty can creep in due to any of these factors. First, it could be due to the observer, the person who is observing it. Like suppose you have a simple pendulum experiment where we measure the time period of this simple pendulum. Now how do we measure the time period? We take it like this here, and then we leave it. We let it go this side and let it come this side, and then we measure the time that it took. That is the time period. Now the observer who is observing it, he may make a mistake in starting the stopwatch or ending the stopwatch. So there could be an error that can creep in due to the observer. So the measurement of the time period would not be an exact, would not be a perfectly accurate measurement. So this is the first source. Now the second is the instrument. Instrument means here you can see this pendulum. Now this could be due to this string. Now if this string is not uniform, what will happen? The tensions will be different, and the formula that the time period that you are calculating, it may change. It may vary because this is not uniform. The velocity may change in between because this is not uniform. So this kind of error can creep in due to the instrument. And the third is the procedure used. What is the process that you are using? Now here you are measuring the time like for one cycle. Suppose someone is measuring the time for 10 cycles and then he is dividing that time t by 10. So he will get a more precise measurement than what someone measures from 1, because there are errors occurring in every time period calculation. Now in this 10 time period calculation, we have error only twice, in the beginning and in the end. So it is actually quite dispersed. Obviously it is not again perfect, but it is quite dispersed. Now this is the qualitative aspect of this. How do we express the uncertainty of the measurement quantitatively? Now as you can see, this is a common ruler that we use all the time. This is in terms of millimeters and centimeters. These larger numbers 15, 16 are centimeters. This is in terms of inches. We will be mainly concerned with this. Now this is delta L. This triangle sign, this is called delta. It is pronounced like this, delta. Now the uncertainty that we call, the error that we called in the length L using that particular ruler is 1 mm. Now if you use this ruler, we know it has a that we call the least count. The minimum length that it can measure is 0.1 centimeter. This we know from the scale. We cannot measure 0.05 centimeter from this, because that will be an uncertain value. We are not sure of it. That will be an uncertain value. We are not sure of this measurement because the minimum graduation that is there in it is for 0.1 centimeter. So the uncertainty that can happen is 1 mm. Means like suppose if you are measuring a length and if it lies something in between these two small graduations like this, like you got up to suppose 9.7 and then you have this something in between the graduation. Now you cannot be sure what it is, whether it is 9.74, it is 9.76 or what the value is. We are not sure of this value. So this is the uncertainty, and this uncertainty is equal to its minimum graduation, means the minimum small markings that are possible. So this is actually plus minus. So the uncertainty is this. Now the uncertainty could be on both sides. It could be either in measuring, it could be higher values or it could be lower values. So we write this in this manner. Now this simply means that the real value the exact value that is there, it is somewhere between 21.5 to 21.7 centimeter. What exactly, that we don't know. Now how to calculate that uncertainty in terms of percentage? Now this is delta L by L, that is the change in length per unit length. This is into 100. This we have converted this into percentage. Now delta L, that is the uncertainty that we saw here, this is actually the graduation of this scale. So this is 0.1, we write everything in centimeter. This is 21.6, it's the length, and when we calculate it comes out almost around 0.5%. So this is how we calculate the uncertainty in the measurement. Now we have seen that for a measurement of a length. Now suppose this is a rectangle. If you have to calculate the area, we know how to calculate the area is L1 into L2, multiply the length and the breadth. Now suppose when this measurement is done, there will be some uncertainty here, because we are using that ruler, there is a limitation to it. This is L1, there will be an uncertainty here, delta L1. Now if you calculate the area, that is L1 into L2, how will this uncertainty factor come in for area? Because if these values are uncertain, the area as a whole must be uncertain. How this will creep in? Now if you write this, if you assume that L1 is this, uncertainty is again the value of the minimum least count of the ruler. Now this is L2, this is 27.9 plus minus 0.1. Now first we calculate these certain values, the product of this certain value that we do, area is L1 into L2, we got this. This is the value 602.6 centimeter square. Now how to factor in this error? This is how we factor in the error in the measurement. We first calculate the error in the measurement of the first length. Now 0.1 is the least count, that's the uncertainty, this is 21.6, we got this. Then we calculate uncertainty for the length second. Then what we do is that the uncertainty in area is actually the sum of these two. Now if we know that the formula is this, we calculate the product of the values by this, but the uncertainties, they add up, they don't get multiplied, they only add up. They only add up. Uncertainties don't get multiplied all the time, they only add up, that's it. So like suppose if you had a volume, so the uncertainty, total uncertainty you can add, now find out, this is this. If you have to find only delta A, you take A to this side and you get the area. This was delta A, 5 centimeter square, and then we write, as we know, area will write the value that you got from the product plus minus delta A, uncertainty that we got. Now suppose you have a volume L1, L2, L3 of a cuboid. What will be the uncertainty in the volume? This will also be like this, delta L1 by L1 delta L1 by L1, delta L2 by L2 plus delta L3, they only add up, total error add up. But when you write this in terms in the real values, the total that is factors in the uncertainty, you have to write in terms of plus and minus, because the error could be on both sides, it could be larger than that or it could be smaller than that. Now we will move to the next topic called dimensional analysis. Now this dimension, what are the dimension and what is the analysis that we will do with the dimension, that we will see in this subsection. Now we know what are units. This dimension is simply an extension of the units, nothing great, nothing new in the dimension apart from the units. So we will see what is that has come in added with this new word dimension. Now L, M and T are known as the primary dimensions. Now as we know that for length the unit is meter, for mass the unit is kg, for time the unit is second. Now when we write in terms of dimension, we write length as L and then we put everything in a square braces. In dimension we put everything in the square braces. This is mass, we write like this, M, and time we write like this. Now this is time t, you can remember it from here. Now if this is L, so for length this is L, if this is mass M, this is capital M, this is time, this is t. So you can remember it like that. These are called primary dimensions because these dimensions will be used very commonly. Most commonly we will use this primary dimension. Obviously there are dimensions For current there is ampere and its dimension is I, but we won't encounter this quite often. These are the three things that we will be using more usually. Now, how to express this? Now we know velocity. We know the unit of velocity. The unit of velocity is meter per second. Now if this is meter per second, we know meter is for length, so we write this as L. Second is for time, so we write as T. Now in dimension we write everything in the numerator, nothing in terms of fractions. This and then put the square braces. So this is the dimension of velocity. Dimension of velocity is Lt minus 1. Now suppose acceleration. We know the unit is meter per second square. Meter is length, so we put L. Second is time, so we put T square. We write like this, Lt minus 2, put the square braces. So this is how we calculate the dimension. So the dimension of acceleration is this. Similarly, suppose force. Now we know force is mass into acceleration. Mass is kg, acceleration is meter per second square. Now if we convert to dimension, the dimension of force. Now this is kg is mass, so it's m. Mass means m. So this is m. Meter is length L. T minus 2, whole thing in the square braces. We don't write 1 here. When power is not given, that means the power is 1. So this is the dimension of force. So this is how we calculate the dimensions. Now what are the uses of this dimension that we'll be seeing the application part of it. First thing is to check the correctness of a given physical relations. Now we have equations in the physics, like a equation I am writing from class 9th, V equal to U plus AT. Now this V is final velocity, this U is initial velocity, this A is acceleration and T is time. Now before I explain this, I will put a question. What if I told you to add 2 apples plus 3 oranges? What is the addition of 2 apples plus 3 oranges? If I ask someone what is this addition, I am sure every one of you will say we cannot add this. The answer they will still say that it is 2 apples and 3 oranges. We cannot add 2 different things. We cannot add apples with oranges. Obviously we can add 2 apples plus 3 apples. Now if we add this, we get 5 apples. This we can do because we are adding similar things. We are adding apples with apples. So this algebraic addition or this same thing is valid also for subtraction. This logic we will be using in this for checking the correctness of physical relations. And as we can see, the sum is also apples only. So these all values must be apples. So if you see this, V is final velocity, U is initial velocity, this is AT. Now this term is added with this term and this is equal to this term. Now as we know, any addition that may happen, any addition for that matter, that must have the same units, or you can call it dimension. We saw dimension is nothing but we gave it the symbols and then we wrote the unit in terms of dimensions. So all of these must have the same unit, then only this relation is correct. Otherwise this relation is not correct. And this should also be equal to the unit of V, because as I told, the sum is also the same thing, the apples only. Now what is the unit of final velocity? This is meter per second, we know. It is final, still that's velocity. So the unit is still same. This is initial velocity, the unit is meter per second. Now acceleration we know is meter per second square. This is multiplied with t, time, that is second. So 1 second cancels out, that is meter per second. What we can see here is that these 3 things, they have the same units. So this is a dimensionally correct physical relation, because we have checked the dimensions only. So this is a dimensionally correct physical relations. Now what is other thing that we can do is to establish a relation between different physical quantities. We can establish a relation, means like this is a relation only. any equation that is a relation, it is the relation between different physical quantities. We can derive a formula like this by using different physical quantities. How can we do it? We'll see how can we solve all this with the detailed examples. Now this is the first example. Here what we'll do is that we'll try to again check the validity of the equation, whether that physical relation is correct or not. Suppose I give you this relation, h is half gt square, this relation I have given you. If I ask the question, is this relation correct or not? Now this relation is for a ball that has been taken to particular height and then thrown and left it. So you don't have to bother about this now, for what, but this formula is given to you. At this stage you have to just only look at the formula. This is h is half gt square. You have to check if this formula can be correct or not. So what we do is that we check that both are apples or not. Definitely the values can be different. Now here this is equal to, so the values must also be same and the dimension unit must be same. They must be both be apples. Now the LHS side we write, LHS is h is height, means it has the dimension of length. Next is RHS, when we move, this is GT square by 2. Now as we know the numbers like 1, 1 by 2, 0.001, pi, all of these numbers, they are dimensionless, means they are unitless, they don't have a unit, they are simply the numbers, dimensionless we call it. So half doesn't have a dimension, this is by 2, dimension is only of g and t square, which are in multiplication. For g we know it was meter per second square, so this is length t minus 2, then this is multiplied with t square, that is t square. So what we get is this L, t minus 2 t square, this gives 1, power becomes 0, this is L. That means LHS is equal to RHS. So we know that this relation is true. Now we'll move to next. Now what are the deduction from this? The first thing, the first application that we have used is that if an equation is found to be dimensionally incorrect, then it is incorrect. Means if you have this value, dimensionally incorrect means the dimension of this is something else, dimension of this is something else. Means we are actually adding apples and oranges. That is not possible at any cost. We cannot add apples and oranges. So if any equation is found to be dimensionally incorrect, then that formula must be incorrect. So suppose I had given you v is equal to u plus a only, and you had not known what the actual formula is. If you calculated, this was meter per second, this was meter per second, this is meter per second square. So you can see that we are adding different thing with different things. We are adding apples with oranges. So this is not possible. So that formula, this formula, you can straight away tell is not correct. Second note is that if an equation is dimensionally correct, it does not necessarily means that the equation is correct. Means, if you see this here, we know the actual formula that we in the class 9 that we did was this. S is ut plus, if you write S as h is ut plus half gt square. Now if you see here, they have given us only h equal to half gt square, the example that I have given here. Now this h equal to ut plus half gt square is the correct formula that we know. This we got, this I have given you an example. Now which of this also you got to be true, this also you got to be true. But it's not possible that you have two formula for the same thing when these values are same. That the h is equal to this also and this also, it is not possible. It is because from the dimension you can check whether everything has the same dimension or not. When you check the dimension, here also, here you will get L, for ut you will get L, this we have got here L. So this is dimensionally correct, this is also dimensionally correct, but the real formula is this. So a formula is, if I write it like this, a formula is dimensionally correct. That doesn't mean that the formula is actually correct. There is a star mark over this, as we have seen here. Both of them are dimensionally correct, both of them are dimensionally correct, but the actual formula is this. So this is our finding, is that if it is dimensionally correct, then the formula is may be actually correct or may not be correct. But if it is incorrect, then I am sure, because then I am adding apples and oranges. So this I am sure. So we have to keep in mind these two deduction from the dimensional analysis. Now we will move to the new topic called vectors. Now what are vectors? We know that vectors are physical quantities that have direction and magnitude. This we know from our primary classes. This is the definition of the vectors. Physical quantities that we talk, there are two types: scalars that we have been dealing all the time, and then there are vectors. These vectors, they have direction and magnitude both. What the scalar has? It has only the magnitude, no direction. Now a scalar, it is completely described by a number, means you don't need to give it to a direction, left, east, north, south, anything. You don't need to give it a direction. Like mass m, if I weigh it on a balance, a particular mass, if it's 5 kg here, it's 5 kg anywhere on the globe. Even if the temperature is high, it is 5 kg. Even if it's moving along east direction, the weight will be 5 kg. If it's moving along west direction, the weight is 5 kg. The mass I am talking, the mass is 5 kg. So it's not changing. Like the temperature, someone is moving, he will still find the temperature to be same. Someone who is at rest, he will still find the temperature to be same. So you don't need to give a direction. By simply putting the number, we can tell that the formula is, that the thing that is given here is clearly defined, clearly specified, and that's what we call a scalar. Now vectors, vector, as I told, it has magnitude and it has direction. Magnitude means the value of it, the numerical value. Like suppose person was here at some point of time and then he moved to here, from starting point to end point. Now the displacement vector magnitude, if we calculate how many steps that he got there, found out that it were 13 paces. But if I only tell that it was 13 paces, then he may have moved in this direction. If I take this as 30 paces, he may have moved in this direction at 30 paces. So these are all 30 paces, but he can land at different places if you don't tell the direction. So if you tell the direction exactly, that it is going in the northeast direction, northeast means exactly in between east and north, that means that 45-degree thing. So then we have specified the direction and we are sure that the particle will reach here only if we measure the length 30 paces. But if you only say 30 paces and don't give the direction, we are not sure where the particle will land after some time. We won't be able to describe the particle, the physical quantity, in a clear manner. Now how do we denote this vector? A vector is denoted either by an arrow on top or by bold print. Like if A is a vector, either I will write like this, or this is A that has been made bold. Now in our lecture we will be using this method, so because we cannot bold it all the time. So this is how it is denoted, a vector. The vector of acceleration, like the example is, it is written like this, vector A. Now the magnitude of a vector is denoted either by the symbol or this, means this is vector A, its magnitude is written either simply A or written like this. Means if you go back here the magnitude is 30, so if you write it here, this is equal to 30, or you can simply write A equal to 30 without arrow sign. There is no arrow sign, that means it is the magnitude of the vector. Now the magnitude of the acceleration vector, like here, you can write this in this manner, or you can write it simply A. Now how do we represent it on a graph, like on the axis that we use, like the xy axis? The vector is represented by an arrow whose length is proportional to the vector's magnitude, and the arrow has the same direction as the vector. Means if it is moving along, suppose this direction, we give this as the direction, and its length, what do you suppose you have to denote 10 meter. Now we know that this is not possible on a graph paper. So what do we do? What we have done in our classes also earlier, that we scale it down. We write like this, we write 1 centimeter is equal to 1 meter. Then what we do is that we draw 10 centimeter and we know that this is 10 meter going in this direction. So we do the scaling, it could be up and down, and then we denote it on the axis. So this is how the vector is written with a sign. Now these vectors that we have defined, they don't follow the rules that we follow in the scalars, like if you have 2 plus 3, this is not equal to 5 in vectors, because the vector comes with the direction. In a scalar, we know this is 2 plus 3 equal to 5. So how do we add two vectors? Why is it that these two are not equal to 5? It's because of the direction. Now this vector R, suppose this is vector A, this is vector B, these are two vectors that we have to add. We denote like this. Vector R is vector A plus B. A and B, R is the sum. Now how to find this vector R? Now if you look at this figure A, we can see this is the vector A and this is vector B. Now the resultant vector, this we call the triangle law. As you can see, it is in the name, that suppose if these two are the vectors, now the resultant vector, the sum of the vectors will be the third vector that will complete the triangle like this. And since you can see the tip was on the tail and then its tip, the direction was going like this, the resultant will be opposite in the direction, means it will be like this. It will complete the triangle and the direction will be opposite to this direction, means at the tip of the first vector A, we place the tail of second vector B. Here you can see, and we join the tail of the first vector A with the tip of the second of the B. This is how we complete the triangle, and this is the direction. So suppose vector A is this, vector B is this is going like this, this is going like this, the resultant will be joined complete and it will be in this direction. Okay. Now similarly, there another name that is given is the parallelogram law. This is actually an extension of this triangle law. Now as we have seen, these are the triangle laws and these are the resultant vectors. Now what is this parallelogram law? Parallelogram law means if this is vector A and this is vector B, what we do is that we draw a vector parallel to this vector B like this and a vector parallel. So by this drawing parallel sides, we know this kind of figure is called parallelogram, which have opposite sides parallel to each other. So if we have drawn this like this, then the diagonal of this is called the resultant vector. But what's important here is that the tail of everything is at the same point. This is the parallelogram law. Now if you see from the triangle law, what we are doing is this was vector A, this was vector B, this completed and this was resultant of this vector. If you make a parallelogram, again this is the diagonal, this is the same line. So both are actually the same thing. Now what do you mean when we say negative of a vector? Suppose you are given this is the vector B, some magnitude is there, it's written on a scale, graph paper, and it is the direction. Vector minus B means it has the first thing, it has the same magnitude as B, means if it was suppose 10 units, this is also 10 units. But vector minus B has the opposite direction. Now this I want to clear it here only. In physics, plus and minus in vectors, they denote the direction. They don't denote magnitude. Means it's not that this 10 unit is greater than this. It's not that the vector B, the magnitude of vector B is greater than minus vector B. It's not like that. It's not like that. The magnitude are still the same, only the direction is different. Plus is one direction, minus is just the opposite direction. So if someone takes this as plus, then this will become the minus. So this has got only to do with the direction, and this has got nothing to do with this value being greater or smaller. It has to do only with the vectors magnitude and the direction. Magnitude is the same, the direction is opposite. Now how do we do the vector subtraction? We have seen how to do vector addition. Now in vector subtraction, what we do is that we are given two vectors A and B. We are asked to determine suppose A minus B. We don't do anything new, we will use the triangle law of addition, and what we do is that we write this like this. Now you can see we can apply the same addition law and we know how to convert B to minus B. So suppose this is a vector A, this is vector B. Now if you draw this, complete the triangle up to this is a plus b, this we know. But we won't do this. We have to find a minus b. If this is b, the minus b will be this. If this is minus b, we can see this is going like this is going like this. So the resultant will be this, and this is a minus b. So we can see what is the difference. How did we get the value of a minus b? By simply using the addition rule. Now the multiplication of a vector by a scalar, like this was vector b, it's given here, this is vector b. What happens when you multiply it with a number like 2, 3, 4, 5 something? So what happens when we multiply with the number, its magnitude changes and the length is still the its length increases and the direction is still the same. If you can see this, these two are still parallel. So the direction is still same, the magnitude has become twice of its length. So if you make this smaller, like if you make it 0.5b, it will become like this. This is 0.5b. Now what happens when you apply with that number that is less than 0, means a negative number or a number that has opposite direction, opposite sign? What it does is that it will reverse the direction. We know when something comes with a minus sign, we simply have to reverse the direction, everything else remains the same. So this is minus 0.5b, if this is plus 0.5b, this is minus 0.5b. Now there is a type of vector that we will be using very commonly, the name is known as the unit vector. Now we know what is unit. We know unit is something that has a value equal to 1. So this is a vector that has a magnitude 1. This vector has a magnitude 1 and it has some direction. Means if you like to draw it on a graph paper, this is like 1 unit and some direction. It could be this, it could be this, anything, but the magnitude is 1. This length is 1 on the scale and its direction could be anything. Because it is a vector, it has some direction. Now suppose we are given vector u and are asked to determine a unit vector small u which is parallel to vector u. What it says actually is this. This is vector u, capital vector. Now you have to find unit direction, unit vector in this direction. How do we calculate it? This is vector u. We can write vector u, you know this is u. When we write without the vector, this is magnitude. And then there is a direction. Suppose I denote this like this, u cap. This direction, I have written the magnitude. For denoting the direction, I write this like this, u cap. So what is u cap? U cap is this vector u by u. This is what's written here. This we can also write like this, modulus of vector u. So this is how we calculate the unit vector. This was vector u. The direction will definitely be the same, and for unit vectors we denote this sign, cap. We denote this by cap. For normal vectors we give arrow at the top. For unit we give a cap at the top. Direction will be the same. Now what are vector components? Now suppose this is vector, any vector v, this is in the plane of x, y. This can be written as sum of two other vectors, one along the x-axis and the other along y-axis. These are called components of vector v. Now this is vector v. Now suppose, think for a second that you don't have that, you have this vector, one vector this and one vector this. If I ask you to add these two vectors, how will we add it? You can either follow the triangle law or you can follow the parallelogram law. If you follow the parallelogram law, then this is simply this, that will make the hypotenuse, this will be the sum of these two vectors. Follow the triangle law, it will still be the same thing, means if it is like this and this was vector, if you move this vector parallel, so this plus this will give this vector. So these two will give the same thing. So now what we can see here is that now this vector, this is the resultant. Suppose if I denote this by r, this is a, this is b. So we can actually write r is a plus b. Now what we can see here that a was totally along x, b was totally along y axis. So we use this idea here. Now suppose we are denoting something, representing something on a graph paper. This is x axis, this is y axis. So if suppose this is Vx and this is Vy. Now what this I and j are? This I and j are unit vectors that we talked just now. What is the direction of I? This is along x-axis. What is the direction of j? This is along y-axis. Means if suppose something is given like this, 30 units along x-axis, so to define this vector we will have to write all of these things, right? 30 units along x-axis, but it's very uncomfortable to write all these things all of the time that we are solving the questions. We will have to write this in every step. What we do is that we have defined a unit vector along this as I cap, this is j cap. I cap means it has the magnitude 1, we know this is a unit vector. Unit is 30. So if I write 30i, then this means that this vector is along x-axis and it has a magnitude 30 units. So we don't need to write all those things now. Simply 30i means 30 along x, 30j means 30 units along y-axis. So suppose this direction component is Vx. Now since this is along x-axis, we put I, and now we don't have to say it because we know now it's I, that means it's along x-axis. Now this is like this is j, Vy, j. Sum of this we know is this vector Vxi plus Vyj. Here I and j are the unit vectors along x and y. Now Vx is also called the projection of vector b along x-axis. Now this Vx is also called, it is the projection of vector b. This is the terminology that we use, is a projection. This x component that we tell, this is called the projection of vector b along x-axis, this is called the projection along y-axis. Now suppose we wish to express Vx and Vy in terms of v and theta, like means suppose this only theta is given, v is given. How do we calculate this x component? Now as you can see, this is like right angle triangle. If this is Vy, this is Vx. Now Vx by v we know is cos theta. The magnitude of this vector v is v. So Vx by v is cos theta. If we apply in this is base, hypotenuse. So Vx is actually equal to v cos theta. So this x component is v cos theta. Similarly, if you have to calculate this, P by B, this is perpendicular, sorry, this is by hypotenuse, V is hypotenuse, Vy by V, this we know since this is theta, this is sin theta. This gives me Vy is equal to V sin theta. So this is the component along y-axis. So we can see it here. This is also called, as we saw here, the projection of V along x-axis. This Vx is called the projection of V along x-axis. This Vy is called the projection of V along y-axis. Now this is Vx, this is Vy. Now since these are perpendicular, this is a right angle triangle. So that is the hypotenuse, we can write it like this, Vx square plus Vy square. V is root over Vx square plus Vy square. Now if I have to find tan theta in terms of Vy and Vx, we know tan theta is P by B. This is perpendicular, this is base. So Vy by Vx. So we got the value tan theta. Now how do we add two vectors algebraically? Means when we are expressing in terms of I, j and k. So what happens, like suppose a vector is given to you, this is vector A. What do we do is that we first break it. Now since this is given somewhere in between x and y axis, so it's not possible to give the direction. So what we do is that since we have I and j, we resolve this, means we convert this to this and this. As we know, if we add these two, we will get here. So what we are doing is that we are going the back step, we are converting this vector A to only this. Now this vector is gone, you have this something I, if I denote is Ax along this is Axi, this is Ayj. What I have done is I have converted this vector in terms of I and j, because we know I is along x axis and j is along y axis. These are defined directions, so we take this. Similarly, we write vector b. If this is vector b, this is Bxi, Byj. Now suppose you have to add these two vectors. Now what will happen in the diagram? This will be A, this will be B, resultant will be this A plus B. We have completed this triangle. This was going like this, so this is the direction. Now what will be the magnitude? Now we know vector C, then we assume that we write it in terms of x and y. Now what will be Cx if we add it? Now this is the component along x-axis. So if we add the components of both along x-axis, the resultant we will get is the component of that. So Ax plus Bx were along x-axis. So Cx means the sum total, the vector sum resultant, his x component is Ax plus Bx. His y component is this. You can see it here only. If you write A plus B, this is like this. J plus this. Now we can write it like this. If we write I things along together, so we have this. This is I plus we have this J. Now the resultant we have written, this is vector C, we have written like Cxi and Cyj. If we write it like this, then that will mean that if you equate the I, we get Cx is this, Cy is this. If you have to calculate the magnitude, we again know if something is along x and y, because we have written C like this. So if something is along x and y, the resultant will be this. Since this is 90, that means this is 90. So we get root over Cx square plus Cy square. Now vector subtraction. How do we do the vector subtraction? Now this is vector A that is given to you. Vector B is given to you. If I have to calculate A minus B, we do the same thing. Dxy, subtract it, and we get the value. If we draw in terms of graph, this is A, this is B, so we can write this like B minus B. This is the resultant, and this is how we calculate the magnitude. We did the same thing. We write D A minus B, so we put two things together, I things together. So this is with minus. So Ax minus Bx, Ay minus By. Now 3D coordinate system. What we have seen here are the two axis system where we were dealing with only x and y axis. Dealing with x and y axis. But now we will deal with things that are in the 3 dimensions. So for describing things in the 3 dimension, we need a third axis called z axis. This axis is like if this x and y are in the plane of your monitor, this z is coming out of the plane of the monitor and perpendicular to the plane of the monitor. This is totally coming outside of the plane towards you. Perpendicular to the plane of the monitor is z axis. Now as we had given I and j for this, there is also unit vector for this called k, I, j, k. They are in the alphabetical order. Now this looks like this. Suppose this is a vector like this, be somewhere in between the air in 3 dimension. X, y and z are this. The magnitude is denoted by this root over Vx square plus Vy square plus Vz square. And this is when you are dealing with only with this plane. In this plane, suppose this is Vx and this is Vz, then this is a right angle triangle. You can see it here. So this length is root over Vz square plus Vx square. Now this is called a right-handed coordinate system. Why is it called a right-handed coordinate system? Is because if you use our right hand like this, if you place this along the x-axis such that this point lies at the origin, and if you try to curl it, our finger, the normal direction of curl is this. This is not the normal direction. If we curl it along y-axis, the direction of the thumb, this is the direction that we are getting, is z-axis. So since x, y, z are like this, that means z is coming along thumb, that means it is a right-handed system. What if it is a left-handed system? What we will do is that x, y will give z along this, because then we have to use the left hand. If you take x like this, you will have to put it in the plane, and you curl along y, z is going in the plane. So that would mean that it is left-handed. So the system that we will be using commonly, and it's given in the questions normally, are the right-handed systems. Now how to check whether the system is right-handed is what I told you. Rotate the x-axis, put your thumb right hand like this. This point should lie at the origin, curl it along this. If the thumb gives the z-axis, that means we have used the right hand. If you do this and got the thumb as the Z axis, that means you have used left hand, that means that is a left-handed system. These are the two systems that we'll use commonly. That's it for guys today. We are done with the chapter of the units and dimensions. Thank you. Having gone through our video lectures and video solutions may have cleared most of your doubts. For any further doubts, you may visit our site www.askIITians.com. On the site, you will find a tab called Ask a Question. Click on that tab. Clicking on the tab will take you to the next page where you will find an icon Ask Experts. If you want to ask any questions, you can select the category of the questions. Like if you want to ask question from suppose wave motion, click on that option wave motion, paste your doubts here. If you want to attach some image of the question, you can attach the image also. Your question will be answered within 24 hours to 48 hours. So students, we have done our chapter of the errors, dimensional analysis and the vectors. I hope you enjoyed. This will be helpful in your question solvings for the JEE Mains and JEE Advanced. For more videos of the chemistry, biology and mathematics, stay tuned to askIITians.com. Thank you.